Okay, so let's get started. Today we will continue to talk about retransmission protocols, and the reason for existence of these is to provide a service which is better than the service below us, just as any protocol. So today we will talk about, last time we talked about stop and wait. Today we will talk about go back N and selective repeat. Then we'll talk very briefly about flow control and framing, and then go into the next topic, which is multiple access. But before we start, some announcements. So next week on Monday is a special lecture. It's the guest lecture where we have 3 experts from e-health, distributed process control, and smart grid. So 3 experts that will come here and talk about their topics. And this is a little bit of a precursor to your choice of third part in the project, which will cover one of these 3 applications. So I strongly encourage you to go there to the lecture on Monday to get some understanding of the basic things in these applications. And then they are an integral part of the course. So it's not just for fun that we have these lectures, and they will be very useful then for the project. The second lecture next week will be online, so it's like a video lecture that I recorded because I will be traveling next week. I won't be here on campus. So it will be available at Ping Pong. So there is no need to go to the lecture hall or something like that. You can watch this at home or wherever you want to do. So there is no need to go here. Actually, there will be nobody here, right? And then the third thing is that we had the student representative course lunch today, or meeting rather. We will also have lunch. So any feedback here is appreciated, and I guess you will circulate some feedback paper. Yeah. Anyway, so we. Okay, excellent. So any feedback on the course is highly appreciated. Right. Okay. So what did we talk about last time? And this picture almost captures everything. So if we understand this picture, we understand a lot about stop and wait. So what do we have here? We have a transmitter and receiver. These are 2 nodes that wants to talk to each other, and they are communicating using a full duplex communication. So information can go from the transmitter to the receiver and to the receiver to the transmitter at the same time. They are separated with some distance, which means that the data or the signal from the transmitter will not instantaneously reach the receiver. So there is some time delay here, which we call the propagation delay. So here's the first bit of a frame being transmitted, and here's the last bit of the frame being transmitted. And the first bit arrives at the receiver at this point in time, and the last bit arrives at this point in time. We assume that there are information frames coming from the transmitter to the receiver, and there are control frames going from the receiver to the transmitter. So these are typically acknowledgements and other things. Right? So just to, this is data, while this is more things that we need to communicate in order for the protocol to work. So these are called control frames, including then acknowledgements. In the information frame, there is NF bits in total. And out of those, NO are overhead bits. So we can think of NF minus NO is the number of bits that the protocol got from the layer above it. So these are the useful data bits for the layer above it. Okay? And as usual, we need to put in some headers and things like that in the transmission. So these are overhead bits, not directly useful for the layer above it. Okay, so it takes some time to transmit this frame. It takes TF seconds, which depends on the number of bits in the frame, and then divided through by R, and R is the bit rate of the protocol or the layer below us. Right? Because what we do as a protocol here, we take this frame and we push that down the stack, and the layer below it takes it and transmits that, and that transmits with a certain rate R. Okay. And then at the receiving side, at this point in time, the receiver starts to process this frame, checks for errors, sequence numbers, whatever. And then at some point, if everything is okay, it transmits back its acknowledgement. and the acknowledgements is typically a little bit shorter than the information frame, because this is a lot of data and this is not so much data. So if this is NA bits, it takes TA seconds to do this, and TA is simply NA divided by the rate again. And then at this point in time, the transmitter knows that starts to process the control frame here, and at this point in time, if everything went well, the transmitter knows that this frame has been successfully delivered. Okay, and then it can repeat this process. Not shown in this graph is retransmissions and so forth. So if something fails here or something fails here, then the frame needs to be retransmitted after a timeout. Okay, so this is the basic transaction. So if it's error-free transmission, which is obviously the best case, what is then the effective rate of this protocol? And the effective rate is the data rate that the layer above us perceives. Okay? And the layer above us transmits a number of bits per frame, and it takes a certain time for this frame to be delivered. The effective rate is the number of upper layer bits per frame, so the bits that we get from above, divided by the total time it takes to transmit one frame. Okay? And the total time it takes to transmit one frame here is it takes from this instant in time until this instant in time, until both the transmitter and receiver knows that this frame has been delivered, and the transmitter can then start all over again. Okay? So even though the frame is actually delivered at this time, the transmitter cannot do anything until this point in time. So this is some type of, what should we call it, protocol coordination overhead. So the total time we should have down here is not TF, right? Because that's not the time which is relevant here. The time which is relevant is the time from when we start transmission of the first bit of the frame until we can start the next transmission on the next frame. Okay. Questions on that, because that's an important concept. Okay. So from the upper layer, they push down bits to us, and we transmit them. And I can accept a new frame every t0 seconds from above, if everything works well. So t0 here is this quantity. So we just then can calculate the data rate for the upper layer, and then also the efficiency, which is the ratio between what the upper layer perceives to what I perceive as a layer. So I get some data rate from the layer below, r bits per second, and then I deliver a rate up, which is the effective rate. And the ratio between these two is a measure on how efficient I am. Right? So we would like to have this high, and this is the number. And then we see there is a certain overhead due to the protocol overhead here. This is a penalty. And then we get a penalty because we have to transmit the ACK. And then there is a penalty here, which depends on the propagation delay and the processing delays. So we see that we get bad efficiency when there are either we have a lot of overhead in the blue frame here, or when we have lots of bits in the acknowledgement, or when this quantity is large. Okay? And this is a ratio of two things. One is the delay bandwidth product. We have some delays here, and then multiply with the bandwidth, which sometimes means data rate, and then divided through by the length of the frame. So to make this efficient, we would like this quantity here to be small, and it's small if either the propagation delay is small, or the data rate is small, or when the frame length is large. The frame length is typically fixed. Okay, an IP packet is a particular size, so we cannot make this arbitrarily large. And what we can do then here is that we can reduce the processing delay, but the propagation delay has to do with the physical distance between the transmitter and receiver. We can't do much about that. Okay? So for certain situations, this stop and wait protocol is not very efficient. And the reason why it's not efficient is because it has to spend a lot of time here. From this point in time to that point in time, it's idle. It's not transmitting any data because it has to wait for the acknowledgement. So to make this more efficient, what we want to do is that we would like to transmit the frame, and then we would like to transmit the next frame already at this point in time, not at this point in time. So that we will see, we can do that with the other protocols that we will discuss later today. But this is at least, this is stop and wait, and it's simple, and it works well as long as this quantity is not too large. Because then the idle time here would be very small compared to the time when we actually are using the channel. Questions? No? Okay. And then what happens then when we have errors here? Well, things will be worse, of course. So if we have a frame error rate of PF, so this is the probability that the frame is not delivered, then the efficiency 1 minus this times the effective rate we get is the effective rate with 0 errors multiplied with this. So we see that when PF becomes large, this becomes small, and the effective rate goes down. Okay, which seems to be correct. Efficiency has the same tendency, the same general expression. It's the efficiency for 0 errors multiplied with the factor 1 minus PF. So when PF becomes large, the efficiency goes down. Okay. All right. So what can we do to suppose stop and wait is inefficient because the idle time, that is the time between this point until we can transmit at the earliest the next frame, if this is significant in comparison to the time it takes to transmit the frame, then we are spending a lot of time as a transmitter being idle, not using the communication resources of the layer below us. So what do? Well, we simply transmit one frame, and instead of waiting for the ACK until we transmit the next frame, we just keep on transmitting frames. Okay, so we transmit maybe 2 frames at the time, or 3 frames, or 10 frames, or 85 frames, or so whatever, right? So we can transmit several frames in parallel. So we have several ongoing frame transmissions. Of course, at some point we need to pick up the ACKs of everything, right, and keep track of things. So, but with a little bit of bookkeeping, we can do this. So this is the simplest scheme, but it's sometimes inefficient. So if we want to be more efficient as a transmitter, we want to transmit several frames in succession, even though the frames that we have transmitted are not yet acknowledged. Okay, so this is called a sliding window transmitter. So we have on layer n+1, this is the upper layer, we have a number of service data units that needs to be transmitted. Okay, and we have some enumeration of them, 5, 6, 7, 8, 9. And so which means that the frames with lower numbers here, we have already, the upper layer has already pushed that down to us. Okay, and we, as a lower layer, we have transmitted these service data units, and we have actually received an acknowledgement from the other side. So we know that these have been successfully transmitted. So we don't store them for retransmission, it's not needed. So these are all the things that have been acknowledged, we have forgotten about them. Currently, we have a number of transmissions which are ongoing, and these are the ongoing transmissions. These are frames which are sent, which means I push them down to the layer below me, but I have not yet heard from the receiver that the receiver has have received these. So these are frames which are in transmission, but currently unacknowledged. We don't know the status of these frames. Okay, and we maintain a buffer in our layer, which is called the send window, and has space here for WS frames. So it's sometimes called the send window also. So in the current send window here, the purple ones here, we have space for 1, 2, 3, 4, 5, 6 frames. However, it might not be completely full with service data units. It depends on the layer above it, how much data they have delivered to us. At the current state, they have delivered 3 frames, or they delivered more frames than these, but I have 3 frames which are ongoing in transmission. This frame, this frame, this frame. Okay. And I need to keep track of these, right? So I need some state variables to keep track of them. So there is one state variable called slast, which is the same as in stop and wait. So that means that the oldest frame, which I have sent, but have not yet heard from the receiver. So it's unacknowledged. It's in transition, but that's the oldest frame. And then I keep track of the most recent frame that I transmitted also. Okay, so this is the oldest and this is the newest frame. But all of these are unacknowledged. And then we have empty space here. Okay. And as long as we have empty space and the layer above us asks us to transmit something, we accept that service data unit and we plug it into the next available slot in the send window. And when the send window is full, then we block the layer above it, of us. We say, okay, I'm busy, I cannot accept any more service data units. Okay, so the basic operation here, we accept service data units from the layer above us as long as there is space in the send window. Once we get the service data unit, what we do is we put that here, and then we increment recent to this number, and then we transmit that frame. So we transmit the frame with the new SDU in it. Once we get an acknowledgement, if we get an acknowledgement for slast here, we slide the whole window one step to the right, which means creates an empty space here and then release the space that we have here, because we have now received an acknowledgement from that, from the receiver. So we know that this has been successfully received. Right? So that's why it's called a sliding window transmitter here. We maintain a window, but we slide it to the right as we get acknowledgements. One thing here which will be, okay, so let's wait with that. And then we retransmit frames. And when do we retransmit frames? When the timer expires. So there is an individual timer for all the things that we have transmitted. And when they expires, we retransmit that particular frame. Okay. So we can see this as almost a number of stop and wait processes which are running in parallel, right? But we need to maintain some bookkeeping in order to keep track of these. Okay. Any questions so far? Is it okay? Yeah? All right. Okay, so this is the main vehicle, right? And now we have two different protocols for this. One which is called go back N, and one which is called selective repeat. And they differ in how the receivers are implemented, the receiver logic. So let's start with the simplest one, which is this go back N receiver. And essentially, it's the same receiver logic as for stop and wait. So it's very, conceptually very simple. Now, before I go through this, I should warn you a little bit, and that is that go back N is not one single implementation and way of doing it. It's actually a family of things with small differences between them. So if you go to Wikipedia, you get one explanation. If you go to book A, you get one explanation, book B, another explanation. They're related, right? But they're not identical. So what I will show now is one way of doing things. It's not the only way to do it. Okay, but it captures the main essence of this. Okay, so go back N receiver. We can think of it that it's already delivered these SDUs and sent acknowledgements of those. And then it's waiting for a new frame. Okay. So it has a receive window here, which is an empty buffer right now. There is nothing in the buffer. It's all empty. And it's waiting for a frame. and it's waiting for a frame with this sequence number R next, just as in stop and wait. Right? It maintains a state variable, which is a number, and that's the sequence number of the frame it expects to see next. Okay. So the receiver doesn't do a whole lot, right? It just waits until it receives a frame, and the frame comes from the layer below it. Okay. Then it inspects the frame, checks for errors. Okay. Now, suppose there are no errors detected, then we go to the next step, and that is to check the sequence number. The sequence number should be equal to R next. That's what we expect. If it's the correct sequence number, so whatever frame we get has R next as the sequence number, then everything is okay. Right? What do? We deliver that up to the upper layer, and then increment R next, and then send an ACK. Okay. If there is an incorrect sequence number, then there are two main ways to handle this situation. Either we don't send an ACK, we just completely ignore the frame, or we tell the transmitter, I received a frame from you, but it has the wrong sequence number. And what to do that is that we send a control frame to the receiver, to the transmitter, sorry, with the sequence number that we expect, which is R next. Okay. So we have already once informed the transmitter that we want R next, and then we get a frame which is not R next, and then we say, oh no, I don't want that, I want R next. So we tell the transmitter this once more. Okay. So that's that option. However, for the sake of explaining the protocol now, we will assume that we do this, which means that the receiver receiving a frame which is error-free, which is good, but has the wrong sequence number, it will simply throw it away and do nothing. Okay. If errors are detected in the frame, we simply throw it away because we can't trust much of it. Okay, so this is the safest thing to do. So we just throw it away. As we will see later on, and this is a point, I will return to this a little bit, but when we send an acknowledgement with a sequence number R next, that implicitly acknowledges all frames which has sequence number less than R next. This will be more important in this selective repeat later on. But if I'm a transmitter and I get an acknowledgement requesting frame number 3, then I know that frame number 2 has been successfully received, right? Because that's what the receiver logic does. Now, if I have 3 frames in transmission here, and I get a request for number 4 or number 5, that means that everything to the left has been received correctly. Right? Because the receiver asks for the next one to put up here. Right? So if it asks for this one, it means that this one has been received correctly, and that implicitly means that this one has also been received correctly. And then we can slide the whole window multiple steps. Right? Okay. So why do we want to do that? Well, because then we have some robustness against lost acknowledgements, right? So if an acknowledgement is lost, it's not necessarily going to trigger a retransmission, as it would always do in stop and wait. Okay, so a little bit of a timing diagram on what's going on here in Go Back N. And then we will assume now that we're trying to use the layer below us as much as possible, which means that we would like to transmit frames as quickly as we possibly can. Okay, so I mean, this analysis is more complicated than for stop and wait because it's more logic in this. So we will present a simplified analysis here, and I will soon point out where we make simplifications. But the first thing we do here is that for highest possible efficiency, we want to transmit frames as quickly as possible. Okay. So how do we ensure this? Well, if we go back to the transmitter here, how many transmissions we can have ongoing depends on the size of the send window. So if the send window is only one frame, then we essentially back to stop and wait. We have to transmit one frame and wait for acknowledgement before we transmit the next frame, and so forth. If we have a very, very large window here, then we are transmitting frames as quickly as we get the frame from above, we send it, right? Because there is always space in the send window. So we will now assume that the window here is very large. It doesn't need to be extremely large, because then it will always be empty at the end, because we cannot transmit frames quicker than the data rate below us allows us to do, right? So, but anyways, what is the rate that we can transmit with? We can transmit with R bits per second, which means that we can transmit the frame every NF divided by R seconds. Okay. First I want to make this point. Make the send window large enough. Okay. To fully occupy the channel, how many bits can we have ongoing in transmission? Well, if we take R times T0, this is the number of bits that can be transmitted in one reaction time. And this corresponds to n frames, where capital N is just a division between this number and the number of bits in a frame. Okay. So just to make clear here, for go back n, it took t0 seconds before we can transmit the next frame, right? So if we want to fully occupy the channel, we would like to transmit frames continuously during t0 seconds. So how many frames can we transmit during t0 seconds? Well, we can transmit these number of bits, the data rate of the layer below us, times the time we have to our disposal. So these are the total number of bits we can ever hope to transmit from this point in time to this point in time. Okay. So how many frames that corresponds to? Well, it corresponds to n frames, which is the total number of bits divided by the number of bits per frame. Okay? So essentially I just counted how many bits can I transmit from here to here. How many bits do I have in a frame? I divide these two numbers with each other. I know how many frames I can transmit during t0 seconds. Okay. So let's start the first frame then. So we transmit one frame, the blue frame here. And it takes TF seconds to transmit that, and it arrives at the receiver at some point a little bit later. So what I'll do next then is that the receiver transmits an ACK back. and the time from here to here is the reaction time, t0. Okay, so for stop and wait, the next frame would be transmitted here. Okay, but let's be a little bit greedy here now and transmit the next. Okay, so here also there is some color coding here. We have a blue frame here, but the acknowledgement here carries a sequence number, the purple one, which requests the purple frame, right? So let's transmit then the purple frame here, but see here that we transmit that actually before we get the request of it. So we're hoping that things will go well here, right? In stop and wait, the purple frame would have been transmitted here. Now we're a little bit greedy. We transmit that right away and hope for good things to happen. Okay, and once this frame arrives here, we get an acknowledgement and it requests the green frame. Okay, but that request comes here, but we transmit the green frame already here. Okay, and then it requests the orange frame, and then we keep on going like this, right? Okay, so far so good. So what happens here if we have an error? Okay, so we transmit the orange frame here, and it blows up somewhere. Okay, the receiver here, according to what we said earlier, does nothing. Okay, so, but the transmitter keeps on transmitting frames, hoping for the best. But these frames here will have the wrong sequence number. So what does the receiver do? The receiver ignores them, throws them away. These looks like nice frames, error-free, wrong sequence number. What can I do? I throw them away. Okay. So what happens here, that after the timeout here, the receiver says, oh no, I did not get an acknowledgement for this frame. I need to retransmit that frame. So you retransmit that. But there will be subsequent timeouts also for the blue and the purple frames here, because there are no acknowledgements going back here. So we have to retransmit more frames now, not only the frame that was actually lost, but actually all the frames that we have ongoing currently. And the reason we need to do that at the receiver here, at the transmitter here, is because the transmitter has no idea which frames have arrived and which have not. It only knows that this one has timed out, and therefore it needs to be retransmitted. How many frames do we need to retransmit? N frames. What is N? N is the number of frames that could be in transmission at the same time before they are acknowledged, right? So we can transmit 1, 2, 3 frames before we get back an acknowledgement of the first frame. Questions? Okay. So here we see that one single frame error will cause N retransmissions. Okay, more retransmissions than what we had in the stop and wait protocol, because then one error just means that we retransmitted that frame. But on the other hand, when things are going well, we are pushing through many more frames per second than for stop and wait. So this is a little bit of an optimistic protocol. But anyways, so when we continue here, we go back, everything works well, and we just keep on going like this. So when things are going well, we are transmitting frames at the maximum possible rate. Right? As soon as we have transmitted one frame, we start the next transmission of the next frame. And then when this is done, we start the next frame, and next frame, and next frame. And as long as there are no errors, this just keeps on going. So it's the best we can hope for. The only problem is when we get errors. When we get errors, we get a pretty high penalty, because we have to retransmit not only what went wrong, but actually everything that was ongoing at the moment. Questions? Okay. So it's a little bit tricky the first time you see it, and it's actually even more trickier when you start to think about it. So even if it looks simple now, perhaps, If it doesn't look simple now, that's okay, I guess, because then you have to study it a little bit further. But if you think this is simple and it's quite natural, don't be fooled by that, because it's actually a little bit more complicated than this. There are some devils in the details here. But you will see this maybe at the exercise and so forth. So anyways, we want to continue now to say something about the efficiency and the effective rates and so forth for stop and wait. For go back N. And what makes the analysis problematic here is that if we look at the blue frame here, what is the probability that that will be delivered? Well, it depends a little bit on what happened before it. Okay? Were there any frame errors before this? So that makes the analysis quite complex, I would say. So we would simplify this by just looking at what is the probability that this orange frame is delivered, assuming that all the frames that were before it was successfully delivered. Okay. So we're going to look at this frame, and then how long does it take before this frame is delivered? And that would tell us something about the frame rate, and therefore the effective rate, and also the efficiency. So we consider the delivery of the first frame, or we can think of it as a frame where a bunch of frames before it was successfully delivered. So there will be no retransmissions due to previous frames, frame errors. Just as in stop and wait, we introduced this variable nt, which is the number of transmissions it takes to deliver the first frame. And that is a random variable because it depends whether there are errors on the channel or not. So let nt, oops. So it's the number of transmissions needed to deliver frame 1, and it's a random variable. Okay, so just as an example, here, if we consider this the transmission of the orange frame here, everything went well in the future. So we can think of this actually as the first frame, if we like. It has its transmission will not be affected by any errors that were before it, right? Because there were no errors. So how many transmissions do we need of the orange frame in order to deliver it here? Well, let's just count. It was one transmission, unsuccessful, and then there was one successful one. So we needed 2 transmissions here, right? If there was an error here, then we need another 3rd transmission here. So this is NT. So NT depends on the probability that the frame is delivered or not. Okay. So however, the total number of transmissions that we need to transmit in order to deliver the orange one here. How many are these? Well, it's one here, and then there are the retransmission of this one, and the retransmission of this one, and retransmission of this one. So actually there's 1, 2, 3, 4 total transmissions needed in order to deliver the orange frame. 3 here, which is n, due to each retransmission event. So whenever we lose the frame, we need to transmit n frames. And then at the end, we need to transmit one more. Okay? So the total number of frames transmitted the total number of transmitted frames is 1, because that's the successful one, and then nt minus 1, and these are all the retransmissions. And for each retransmission event, we need to transmit n frames. Okay, so we need one transmission event for the successful delivery of frame 1, nt minus 1 retransmission of frame number 1, and then n is the total number of retransmissions, including the one that was in error. So here there are 3 retransmissions, but there is only one error that caused this. Okay. Good. So now we're ready to compute then the time for delivery. So the time to deliver frame 1, let's call that t, and then g bn, so go back n. So this is the time it takes to deliver a frame and go back n, or the first frame actually. So that is simply the time to deliver one frame times the number of frames that we have transmitted. So it's tf times 1 minus 1 plus n minus nt minus 1 times n. Okay. So nt here is the number of times we need to transmit frame number 1, okay, including retransmissions. So it's a random variable, and we had that random variable in the last lecture also. So if we assume that frame transmissions are independent of each other and they fail with probability pf, we know that the expected value of nt minus 1 depends on the frame error probability as follows. It's pf divided by 1 minus pf. Okay. So this we did in the last lecture, so I won't repeat the derivation of it. So if we're interested in the expected value of the go back n delivery time, we just take the expected value of this. The only thing which is random is the number of transmissions. So the average, the expected value of tgbn is simply by taking the expected value. Let me do this. So it's tf 1 minus nt, the expected value of n. The expected value of nt minus 1 times n, like this. So this is tf 1 minus, and then instead of the expected value of nt minus 1, we put in pf divided by 1 minus pf. So pf 1 minus pf times n like this. And then we simplify this to be Tf 1 minus Pfn divided through by, let's see, how do I do this? How do I want this? 1 minus Pf. I think I messed this one up. It's 1 plus n minus 1 Pf divided through by 1 minus Pf. Okay. So now we know the expected time it takes to deliver one frame. So it's this expression here. It depends on Tf, and it depends on this parameter n, and it depends on Pf. So the effective data rate for go back n, what is that? Well, it's the number of useful bits we have been transmitting. And the number of useful bits is nf minus the overhead bits. Okay. So this is the number of bits in the service data unit, nf minus no. And then we divide through by the time it takes to deliver this one, the average time. And this is the average time. And after a little bit of algebra, we can write this as 1 minus Pf, 1 minus No divided by Nf, and divided through by 1 plus R T0 divided by Nf, Nf minus 1 times Pf. Okay, but I think before interpreting this, let's take a break for 15 minutes.